All right, this lesson is called Lesson 4, Unit 4, Lesson 5, Electron Configuration. It typically takes 3 days to really master this. So this video will be broken up into 3 parts. This will be part 1. And this diagram you guys are looking at is what you did at the very end of Lesson 4. So I need to teach you a few things, some of the basics about this topic before I can really get you rolling. I like to view today as the training wheels day, where you hardly know how to do it, so you need a lot of help. And that's part of the process, all right? So when it comes to electron configurations, there's going to be a way to actually identify every element based on the number of electrons that it has. So I want to get something very clear with all of you. What's up? Okay. You gotta go. Let's make something abundantly clear. I want to zoom in on this periodic table. Oops, that's a little too broad. This element is titanium. What is titanium's atomic number? Oh, that's not titanium, that's vanadium. Okay, let's do vanadium. You never heard of it before, just go with it. What is vanadium's atomic number? Very good, 23. What does that atomic number represent? Varun? The number of protons. Now, all of these are atoms. The definition of an atom is something with a neutral charge. The proton number equals the electron number. So if vanadium has 23 protons, how many electrons does it have? And the crowd goes silent. The definition of an atom is something that has a neutral charge. That means no positive, no negative, it's nothing. So if vanadium has 23 protons, how many electrons does it have? We don't have time for me to ask the same thing twice, because all of you got it that second time. Let's try this again. Potassium is element number 19. How many protons does it have? How many electrons does it have? Hydrogen is element number 1. How many protons? How many electrons? Okay, I think we're ready. So at the end of yesterday's class, you made this. If you have highlighters out, get them. If you don't have highlighters, improvise. Every section of the periodic table, I've colored. I have red, green, purple, and blue. These sections are using letters, okay? So that and all of you, take your AirPod out. Helium over here. This is called the S block. It is columns 1 and 2. Now this will be the next 3 weeks will be the most you've ever looked at a periodic table in your whole life. So I got to get you familiarized with it. I want you all to look at something. Helium should have been right there. Should have been, but it isn't. But pretend that it is. Helium is part of the S block. That's why I highlighted it in yellow. It is part of the S block. After S comes the P block. After P is the D block. And then finally, down here is the F block. Now to finish numbering, the D block has columns 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many total blocks is that? Or columns is that? That's what I meant to say. How many columns is that if you go from 3 to 12? 10. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10 blocks, or 10 columns, excuse me. Over here, we have 13, 14, 15, 16, 17, 18. How many columns is that? 6. And then down here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These columns are called groups. And so from this point forward, I'm going to be referring to them as groups. So a column on the periodic table is a group. That's actually a vocab word for your next unit. So it kind of helps you to just get that out of the way. So let's see if you guys are following along. Nella, how many groups does the S block have? Right. Alex, how many groups does the P block have? Correct. Kanan, how many blocks does the D, or yeah, how many groups does the D block have? Sorry, I meant to say Kellen. 10. And Madeline, how many does the F block have? 14. Are you guys with me so far? Okay. Now, hold on a second, let me get something straight. A group is referred to as a sub level. A block is referred to partially as an orbital. So you're going to do some mental math here, okay? I've got the S, P, D, and F. I got a little catch here. Each sublevel can hold 2 electrons. All right, hold on. Now, I want you guys to make a little amendment here. Right over group, put every pair of groups. There we go. That should make it all better. Every pair of groups can hold a maximum of 2 electrons. So I want you to take a look at the S block for me. Now let's say that the S block has a total of 2 columns, 2 groups. The maximum number of electrons that it can hold is 2. Oops. So this would be the max number of electrons. What is the maximum number of electrons that the P block can hold? Alex? 6. Madeline, how about the D block? What's the maximum number of electrons that the D block can hold? 10. Kaylin, what's the maximum number the F block can hold? 14. So each sublevel has, we got 1, 3, 5, and 7. These little boxes I'm drawing are where you're going to actually write your electrons into to make these configurations. Again, this will all start to, I know this is as clear as really thick mud. It will get clearer and clearer as we go. Yes, Varun.
You said each sublevel can have like 2 electrons, right? So if the S block has 2 sublevels, wouldn't that mean it can have 4 electrons total?
It actually can just have, it can only have 2 electrons. It can have, I think I got that crisscrossed, but I'll get it straightened out. There's one, every sublevel can hold 2 electrons. So let's put it like that. Right there. Every sublevel can hold 2 electrons. So there's 1 sublevel in the S block, it can hold 2. There's 3 sublevels that can hold 6. There's 5 that can hold 10. There's 7 that can hold 14. There's 1 sublevel. So I think I misrepresented that. So you can ignore that part. I'll fix that. Sorry. All right. You guys are going to get a lot of practice with this. So here we go. All atoms, whether you're big old hydrogen, or sorry, small hydrogen, or something big like uranium, they can all be described based on the number of electrons they have and where they're located on the periodic table. Whether they're in the S block, P block, D block, F block, it doesn't matter. The size of the atom or the number of electrons makes no difference. So the size of the atom and the number of electrons is inconsequential. For electron configurations, the arrangement of electrons in an atom is basically what the configuration means. What I'm going to be teaching you over today, tomorrow, and Wednesday is how to actually write the configurations. It's going to be like a code. I got to teach you how to make that code. When it comes to writing electron configurations, there are 3 rules. Number one, these are also vocab terms. The off-ball principle. This states that the electrons occupy the lowest energy level first. So what this generally means in plain English is whenever you are doing an electron configuration, no matter what element I assign you, you have to start from the very beginning. You guys are living in the year 2023. I know you've heard of things like Nintendo and Super Mario. When the original Nintendo came out in like the mid 80s, I had one and I had Super Mario 3. Every time I turned on my Nintendo, I had to start that game from the very beginning. There was no such thing as a memory card or saved data, or do you want to save your progress? You didn't have that option. You had to start over level 1, stage 1 every time. You couldn't just pick up where you left off. You're going to have to do that with this. So from the very beginning, you got to start at hydrogen and work your way all the way to whatever element that I give you. So in plain English, this generally means you must start from the bottom and work your way up. Rule number 2. Is the Pauli exclusion principle. You have 2 electrons max in an orbital. But they're spinning in opposite directions. When it comes to the Pauli exclusion principle, electrons are represented as arrows. And we are going to draw them like this. We could do this, guys. Listen, you could do this. Technically, that's what you should be doing. I'm going to make it easy for us. Rather than do this and do this, we're going to do this. It'll make it easy. Trust me. Now, how do you draw this? Well, this is an electron spinning in one direction. This is an electron spinning in the opposite direction. This is an unoccupied orbital. No electrons here. And this is a filled orbital. You have 2 oppositely spinning electrons. I want to make a little asterisk here. I'm not going to write this down, but I will tell you guys the second one right here, you'll never see that just by itself. In order to have an arrow pointing down, you're going to have an arrow pointing up first. So you'll never have an arrow pointing down by itself. That will never happen. I just want you to see what an oppositely spinning electron will look like. Okay, and the third and final rule, it's called Hund's rule. Electrons with the same spin must occupy the equal energy orbital before additional electrons with opposite spins can occupy the same orbitals. That's a mouthful. So unless you take a moment to jot that down, I'll tell you what I mean by that. Okay. A few more seconds, and I need you all to be looking up. We're going to be doing a lot of different examples. Right now, I still don't expect you to have any idea how to do this. But once I start getting you going, you're going to start to get a better grasp of it. Trust me. Trust the process. So check this out. Here's what Hund's rule says. Please pay attention. You are not to do this. You don't do what I'm about to show you. So everybody look up. You do not do this. That is not the method in which you write electron configurations. What he's saying is you have to have all the electrons that spin in the same direction. And after you've maxed out all the electrons that spin in the same direction, then you can go back and have electrons spin in the opposite direction. So look this. Up, 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 down, down, down. That's how you do it. So I'll do that again. When you're drawing electron configurations, you have to have all the electrons that are spinning in the same direction on an orbital first. Up, up, up. Okay. Then you go down, down, down. That's how you do it. Yes.
You had 3 ups and 2 downs.
Okay. So when you get an example, imagine what would look like. Chlorine would look like that. I know you have no idea how to do this yet, but here's how aluminum. No. Here's how phosphorus would look. Up, up, up. And then sulfur would be 4, chlorine would be 5, and argon would be 6. But you have to go up, 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 up in one direction. If it was the D block, guys, and you had 5 of these boxes, you would still have to go up, 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 up before you're allowed to go down, 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 down. What the moral of the story here is that you have to make sure you include all the electrons that are going in the same direction first. You can't start going down until you filled out all of them that can go up. And remember that the Pauli exclusion principle says you can only put 2 in a box at a time. So one more time. Up, 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 down, 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 down. Yes, Aiden.
You show one that has 7?
It would be the same thing. I would go, look at me. Up, 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 then down, 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 down.
No, I'm saying like, in that box, would you go up, up?
Well,
up,
if it's
up?
7, you have to have 7 boxes. It would still go, it would
I'm
be,
talking about like 7 arrows in that box.
oh, like, okay. That's 7.
Alright.
Yeah, you go up 5 times, down twice. Okay. I see what you're asking. All right, now, electron arrangement. After this, we'll start to get some practice in. Okay. I'm going to give you guys the easiest element in the universe. What is it? Hydrogen. Okay. We're going to do hydrogen as our first example. You got to start small. So, take a look at your periodic table. What block is hydrogen in? S. What row? Not column, row, sideways. We call that a period. What period, what row is hydrogen in? 1. What column or group is hydrogen in? Here's the notation. 1, S, 1. We're going to teach you how to do this. Again, if you don't get it, you're not the only one. There's 31 of you. No one's probably getting this yet. That big 1, that coefficient, that is a quantum. It is also known as the principal energy level. You know what number to choose based on the row that it is. And the row is actually called a period. The S stands for the subshell or the block. And this is also called a sub-level. And that little 1 right there is the number of electrons. In that quantum and subshell. So I have you all for about 7 more minutes because it is a Monday with 10-minute homeroom. This is all we're going to do on tomorrow's class. Like, this is all of it. So I want to start doing some practice. I want to do hydrogen again. We're going to have the electron configuration. And you're going to have the orbital diagram. And this is going to take all day tomorrow and part of Wednesday. All right. Ready? Here we go. What principal energy level is hydrogen found in? 1, 2, 3, 4, 5, 6, or 7? And when I ask you what principal energy level, I'm basically asking you what row it's in. What row is hydrogen in? Good. 1. Next question. What block is it in? S. Write an S. Now, first, there's 1 electron per column, per group. How many electrons does hydrogen have? 1. That's it. 1s1 is hydrogen. Now, when you're drawing it, you could fit, check this out. I want you guys to think. you can fit a maximum of 2 electrons in this box. This box represents an orbital diagram. 2 electrons max. Look back up here. How many total columns or how many total groups is the S block? 2. So how many electrons? You can fit a maximum of 2 in here for the S block, but how many electrons does hydrogen have? So you're just going to put 1 up arrow, and that's it. That 1 is not a number 1. That 1 is an arrow. Or that's not even a 1. That symbol is an arrow. I want you to now do helium. I'm going to help you out here. This is Train Wheels Day. What principal energy level, aka rho, aka period, is helium found in? What is it? 1. What block? How many total electrons does helium have in principal energy level 1 in the S block? 2. How many orbitals are there in the S block? Like these little boxes. This little box right here is an orbital. How many boxes or how many orbitals do you have for the S block? Just 1. How many electrons can you fit on 1 orbital? 2. So how many total arrows will I have, which represent electrons, in this orbital for the S block? And what direction will they be spinning? Will I have 2 up? Will I have 2 down? Will it go down, up? No. It goes up, down. We're going to continue to practice every little bit. You got to chip away at your misconception. Ask questions. You always do up first. I was trying to make sure you knew. I was just asking a question to eliminate the possible choices that would be wrong. You never go up, up. You never go down, down. You never do down, up. You always do up first, then down every single time. Yeah. A sub-level is going to be the blocks, the S block, the P block, the D block, or the F block. Anything else, Aiden? We're going to do them all. We're not all 118. We're going to do a lot. We're going to build our way up, okay? You want to do number 11. Let's build there, okay? So let's do lithium. I want you guys to find lithium on your periodic table. I'll ask you a few questions, okay? What principal energy level is lithium found in? No. 2. It's in the second row. What block is lithium found in? Good. And how many total electrons does lithium have? 3. Okay. Now, we're going to a second row here, so we're going to have to do a little bit more. But I want you to go back to, was it Aufbau's rule? It was. You have to start from the very, very bottom. So let me ask you this. Here's how I like to phrase this. In order to get to lithium, which is element number 3, what elements do you have to go through first? Hydrogen and helium. So you have to do those. So 1s2, which accounts for hydrogen and helium, that's both of them. 2s1. I'll break it all down for you. This right here, 1s2. What elements does that represent? Hydrogen and, because in order to get to helium, what did you have to go through first? You can't get to helium until you've gone through hydrogen. You have to start in the ground state first. And then this represents lithium. 1s2, 2s1. I want you to add these numbers up. This might be the last time we have time for. What is 1 plus 2? How many electrons does lithium have? those exponents should always equal the number of electrons for the element that you're doing. We'll have to stop there. I still expect it to be very confusing. All we're going to do tomorrow is just practice. That's it. Straight up practice. No new notes. No new rules. All practice.